Hello, my name is Matt Morgan. Thank you for tuning into my talk. I'm going to be talking about integrated warm electronics for the next generation very large array. Here, I just want to acknowledge briefly the people who've contributed to this work, my colleagues at the CDL in Charlottesville. This slide shows the frequency coverage of the instrument. NGVLA operates from 1.2 to 116 gigahertz in 6 feed and LNA receiver bands. The first 5 bands, or the first 5 feed LNA pairs, operate from 1.2 to 50.5 gigahertz, skipping over the oxygen absorption band between 50 and 70 gigahertz, and then there's a 6th receiver band at 70 to 116 gigahertz. The integrated receiver packages comprise 16 modules. The first is a direct sampled module that provides the first baseband Nyquist zone from 0 to 3.5 gigahertz. The remaining 15 modules are sideband separating down converters utilizing spaced discrete LO frequencies that allow the upper and lower sidebands of adjacent modules to overlap. The first 5 bands are digitized to 8-bit resolution, whereas the 6th receiver band is digitized to 4 bits, allowing more bandwidth to be covered with fewer modules. This slide shows the frequency coverage in tabular form. The first column is the band number, and the second column is the RF frequency range for each of those bands. The receiver type is identified in each case, where DS stands for direct sampled and 2SB stands for sideband separating. The first 5 bands, which digitize at 8-bit resolution, sample at a rate of 7 gigasamples per second, whereas the 6th receiver band, which digitizes at 4-bit resolution, samples at a rate of 14 gigasamples per second, giving an aggregate serial rate in each case of 56 gigabits per second. The local oscillator frequencies are fixed tuned, each is a multiple of 2.9 gigahertz, and the upper and lower sideband frequency ranges are shown in the last 2 columns, illustrating that the bands stitch together continuously without any gaps in each receiver band. In this slide, I'm showing how the bandwidth in the previous table was obtained. In the 8-bit bands, for example, we're sampling at 7 gigasamples per second, giving us a Nyquist limit of 3.5 gigahertz. You can see the bandpass shape of the low-pass filter in black crossing over that Nyquist limit and giving us some aliasing highlighted in orange. While all of this bandwidth is delivered to the back end, we only count the good bandwidth free of this aliasing corruption up to about 2.9 gigahertz, and our local oscillator tones are spaced at multiples of 2.9 gigahertz so that the lower sideband of the next higher receiver band overlaps at that frequency, and we don't have any gap in coverage, only a small dip in signal-to-noise ratio as the roll-off of the filter. This is a comprehensive subsystem block diagram. The only thing I'm going to highlight here is that for those bands that deliver more bandwidth than can be processed in a single down converter module due to limitations of the bandwidth of the digitizer, we have some power dividers highlighted here in orange to split the signal from the front end feed and LNA into multiple channels so that more than one module can process them. This is one of the early engineering prototypes that we built in S-band covering 1.7 to 2.6 gigahertz. It gives you an idea of the size scale that we're targeting for each of the receiver modules on the NGVLA. The digitized bandwidth in this case is 622 megahertz. It is a sideband separating module and includes all of the conversions from RF to baseband, from analog to digital, and from copper to fiber in a single module with consuming only 4 watts per polarization channel and delivering its output data at 2.5 gigabits per second per lane on a 1310 nanometer single mode fiber. Next, I'm showing a W-band engineering module that we built. This particular module is actually a lot larger than we planned to build for NGVLA because we're using off-the-shelf parts, and particularly in the analog to digital converter and serializer section, we have a plan for a custom ASIC development that's going to make that part a lot smaller, and this whole module will be more on the size scale of the previous S-band module that you saw. But it gives you a good idea of how these modules go together. We have an interior sort of high-frequency electronics part consisting of RF MMIC chips, some custom, some off-the-shelf designs. We have an IF circuit board which does most of the baseband signal processing, and then a digital photonic circuit board which contains the digitizer and fiber optic output. Band 6 is the hardest band to find suitable off-the-shelf mimic chips for, so I'm having to do some custom design. In particular, on the left here is a custom wideband IQ mixer, which I've been iterating on with United Monolithic Semiconductors using their gallium arsenide Schottky diode process. On the right is the amplifier I plan to use. I was going to do a custom design here as well, as I couldn't initially find one that was suitable, although I recently became aware of this 70 to 130 gigahertz amplifier from Teledyne. It's an indium phosphide HBT chip. A little higher noise figure than we were targeting for NGVLA, as this was mostly designed as a power amplifier, but it should be acceptable since this is preceded by a cryogenic gain stage. Lastly, I'm thinking I might need a step attenuator for the RF. I have IF step attenuators right now, which I can use in a pinch, but they're not preferred since we're calibrating the amplitude and phase of each to do calibrated numerical sideband separation. It's preferable to have one step attenuator in the RF path before you divide to I and Q channels for IF. The S-band and W-band modules, which I showed you earlier, were actually early prototypes designed before the NGVLA receiver bands were set down. The next one I'm going to talk about, the band 3 module, is the first one that was actually developed specifically for the NGVLA. One thing I want to point out about it is that the serial ADC will be a first generation prototype. If you recall, I said that we were going to develop a serial ADC operating at 56 gigabits per second per lane output. But that's going to be a fairly expensive development that won't come until fairly late in the design and development cycle for NGVLA. So this module will be built first with a first generation prototype operating at 10 gigabits per second serial output. This is a preliminary mechanical drawing of the band 3 module, so you can see where we're at this point. On the right is an image of the interior showing the high frequency mimic section. On the left is an animation showing an exploded view of the module, so you can see how the parts go together. We have the high frequency section in the middle, we have the low frequency IF circuit board below that, and we will have the digital photonic portion in the upper cavity that was first opened up in this animation. The digital electronic circuit board has not been laid out, so that's not yet included. We do try to keep the analog and digital parts separate to avoid self-interference from the clock edges, so that since the analog portion has a large amount of gain, we don't want to amplify those clock edges and have that show up in our output spectrum. This is a conceptual diagram of a typical analog, digital, and photonic signal path, starting with an analog front end driving an ADC, which delivers parallel data to an FPGA microprocessor or CPLD, and a serializer to drive the laser driver under the fiber link, which is picked up at the other end by a photodetector and another FPGA. In typical systems, there's a great deal of link management in the front end, including bit scrambling, 8B, 10B encoding, packetizing, framing, and other forms of protocol overhead. In addition, there's a huge cost in terms of power and footprint associated with the parallel interface between the ADC and the FPGA, and these are the issues that we'd like to eliminate with our custom unformatted serial link and ADC solution. By eliminating the high-speed FPGA or CPLD, we can integrate the ADC and the serializer together as one unit, and we defer the link management functions to the receive end where you can have an FPGA without the constraints on power and footprint that there are inside the antenna. When we integrate these two chips together, we get a huge reduction in footprint and power dissipation. And this is the part we're calling the serial ADC, which is a high-speed digitizer and serializer in one, having an ultra-low power and ultra-small footprint. So the rationale behind why this is beneficial is illustrated in this slide. This is a typical layout of two ADCs for I and Q channels driving a serializer. And as you can see, the ADC die itself is typically fairly small, as evidenced by the ground pad on the ADC package. But it has to deliver its data on parallel output pins, which requires a great deal of space on the circuit board. In addition, the driver between the ADC and the serializer is typically an LVDS transmission path using a driver and a receiver, which is really a terminated transmission line. They do this because they don't know when you go off chip how long the traces are going to need to be, and what the standing waves might be from reflections, so they want to terminate the far end of the line with a resistor, but this wastes a lot of power. By integrating these components on a single chip, we can use transistor to transistor logic, which is a lot more efficient, while eliminating the huge parallel interface and leaving us with just analog differential pairs as the input and a differential serial output, which reduces the footprint on the circuit board dramatically. And so this illustrates the amount of size reduction that we expect to get. On the left is the W-band module containing the FPGA and ADCs to do the digitizing and serialization functions, as well as a bank of power supplies to provide all the different power rails that the FPGA needs. This whole thing can be replaced with a very tiny custom ASIC chip fitting in a 5mm QFN package as shown. Prototype modules using this custom unformatted serial link have been successful. These include the S-band and W-band modules, which I showed you earlier. Shown here on the right is the GUI that we use in our test systems. When we're running the unformatted serial link, there's a bank of green lights down at the bottom showing that all 6 channels are locked on and running synchronously. There's raw sample data in the blue time series diagrams, and then histograms on the right showing the prevalence of samples from each channel. But these prototypes don't realize the actual size, weight, and power benefits that we can realize with a custom ASIC. That custom ASIC has been under development. This is an illustration of the layout and some of the key specifications. This is the first generation prototype that we're building. It's a 2-channel chip with a serial output rate of 10 gigabits per second each for the 2 channels. Since the interface, the input analog and output serial lines don't have any dependence on the bit resolution, that's actually an adjustable feature. You can program it to sample at 2, 4, or 8 bits per sample, giving you sample rates of 5 gigasamples per second for 2-bit sampling, 2.5 gigasamples per second at 4 bits, or 1.25 gigasamples per second at 8 bits. And in all of those modes, the power dissipation is only 167 milliwatts per channel, which is very low for an ADC and serializer built together. And the whole thing fits in a 1.5mm square die, roughly square die, and fits in a 5mm QFN package. The second generation ADC, which we will develop for the NGVLA, will be similar but contain 4 channels and a serial rate of 56 gigabits per second with bit resolutions of 4, 8, and 12 bits per sample, giving us sample rates of 14, 7, and 4.6 gigasamples per second at 4, 8, and 12 bits respectively. And this will be in a more advanced process node from which we expect to get even more savings in power dissipation on the order of 100 milliwatts per channel. We believe the die will probably be about 1 millimeter square and will fit in a 6mm QFN package limited by the pin count that we'll need. This is a photo of the serial link test bench in our lab at the CDL in Charlottesville. This is actually a complete receiver mock-up from the cryogenic input all the way through to the digital output, the fiber link, and the GUI, which you can see at the top left there. The actual module under test is the W-band module that I've shown you pictures of earlier. It's actually not in view in this picture. It's just around the other side of the doer where it says IRD integrated front end. There's some custom RF and local oscillator test sources that we also built custom in our group in this lab. The digitized data is carried by fiber, where there's a 10-kilometer fiber spool shown in this picture. We have since upgraded that now to a 40-kilometer spool of fiber to test some long-distance fiber optic links, all using this custom serial link that we've developed. And then there's a back-end FPGA, which is sort of our proxy for the NGVLA correlator. Unfortunately, I have to report that the ASIC development contract ran into some problems due to mistakes on the part of the contractor. The parts that they delivered to us didn't work, and we worked with them to figure out that they forgot to connect the power supply to the on-chip serializer so that it wouldn't power up. Also, the clock reference input was attached to a 2.5 volt logic gate behind a 1.2 volt ESD clamp, so there's really no way to get that reference signal into the chip. We have to bypass it and are unable to use the chip in its primary operational mode. Lastly, the state machine for the monitor and control interface to the SPI bus was faulty in such a way that there's no way to read out the registers without actually changing their state. And unfortunately, none of these problems were revealed by the simulations presented to us during the design reviews. So we're working with them to correct these mistakes. So that completes my talk on the status of the IRD development for NGVLA. Thank you for listening, and we'll welcome any questions that you all may have.